Hello and welcome to the launch webcast for our 49th Electron mission, set to launch from Pad B at RocketLab Launch Complex 1 in New Zealand in just under 19 minutes from now. Today we'll be launching the second of two launches for NASA's climate science PREFIRE mission after standing down a couple of days ago due to out-of-bounds LOX temperatures. Thanks for joining us. My name is Murielle Baker and I'll be taking you through today's countdown to liftoff for the PREFIRE and ICE mission, currently set for launch today at 3:15 p.m. local time or 03:15 UTC. Now, PREFIRE and ICE is the second of two back-to-back launches on Electron to deliver NASA's satellites to orbit for the PREFIRE mission. PREFIRE stands for Polar Radiant Energy in the Far Infrared Experiment, and it's a mission designed to measure heat loss from the Arctic and Antarctica to help improve climate and ice loss models that better predict Earth's ice, sea level and weather changes. The first satellite in the PREFIRE mission was deployed by Electron to its 525-kilometre orbit 11 days ago. After today's second launch and deployment, the two PREFIRE satellites will spend the next 10 months crisscrossing Earth's coldest regions to collect their data. And once they're operating, PREFIRE will make the first full spectral measurements of far infrared radiation, revealing the full spectrum of Arctic radiant energy. Now, those measurements will then be used in climate and ice models to help better predict Earth's sea ice loss, ice sheet melt and sea level rise. PREFIRE is focused on the Arctic and Antarctica because these polar regions have a big influence on the Earth's temperature. Excess heat escapes from there to space, and the difference between how much heat is released versus how much heat is received from the sun in the tropics is a key influence on the planet's temperature. Better understanding this process and what it means for Earth's future climate is what the PREFIRE mission is all about. Here's NASA to explain more.
The Arctic is warming 3 times faster than anywhere else on Earth.
This is a huge problem, in part because that is enhancing melt of the ice sheet. It's leading to enhanced melt of sea ice.
All of the coastal communities around the world are now seeing sea level rise around them and experiencing increased flooding.
It will impact the future generations. They're going to inherit a planet that's going to be many degrees warmer than what we are today.
We need to have better predictions of how sea level will change, how the weather around the planet is going to change. The only way we're going to do that is to understand how the polar regions are responding to climate change.
We have this considerable knowledge gap in our understanding of Arctic climate.
PREFIRE is going to fill this important gap.
PREFIRE, Polar
Radiant
Energy
in the Far
Infrared
Experiment.
So Earth's temperature is set by a balance between the amount of energy the Earth receives from the sun and the amount of energy that it emits back to space.
Most of the energy that is radiated to space from our polar regions is far infrared energy, and we have no modern satellite observations of this incredibly important energy spectrum. PREFIRE will be deploying 2 CubeSats. Over the course of a year, they're going to be measuring the far infrared energy for the very first time that is leaving the top of our atmosphere.
Each of our PREFIRE CubeSats carry something called a thermal infrared spectrometer that looks down at the Earth and gathers energy being emitted from the planet at different wavelengths.
Just imagine a rainbow. When you see a rainbow, you see the different colors in the rainbow. And what happens is light gets dispersed. Similarly, we see the different wavelengths split up, and you can measure each of these wavelengths. And that's what the spectrometer does. It spectrally separates the radiation into different wavelengths.
These wavelengths were going to give us really important information about how the surface is changing in the polar regions, whether that's going from an ice-covered surface to a melted surface, or whether it's going from sea ice to open ocean.
The 2 satellites are going to be orbiting in a polar orbit around the Earth. The first satellite comes along and measures the scene over the poles. And then a few hours later, we have the second one come along in a different orbit and measure the same scene so you understand the impact of how the energy changes in those few hours.
It's really important that we understand how much energy is being emitted by the polar regions, because that defines how cold the polar regions get. And that temperature difference between the warm tropics and the cold polar regions is actually what drives the entire weather system around the planet.
What we want to do with PREFIRE is we want to take these new observations that have never been made before, and we want to improve our understanding of the climate system and improve our understanding of how climate is going to be changing.
Understanding how the sea level rises and how the ice melts is going to help us understand weather events, and that's going to have direct impact on our farmers and agriculture.
There's a real urgency to getting this information now. Things are changing so quickly in the Arctic that we may only have 5 to 10 years to respond to those changes and help protect the property and lives that may be affected by that.
Launching the PREFIRE mission for NASA represents a bit of a full circle moment for Electron, because it was around this time last year that Electron launched a constellation of small satellites for NASA for a mission called TROPICS that was focused on the regions of Earth surrounding the equator, helping weather researchers understand more about the environmental factors that contribute to hurricanes there. So, from the tropics to the poles, Electron has been behind NASA's small satellite missions that teach us more about our environment and the world around us. Now, shortly, today's operators will be polled for their launch readiness in the final go, no-go poll run by our launch director, Julia Wembacher. That status check begins at the T-minus 12-minute mark to liftoff and goes through each operator on console in our Mission Control Center and in our Range Control Center at the launch site. We're coming up to the poll now, set to begin in just a few seconds.
And to all operators, alien mission code, we're proceeding now with the go, no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Recon.
Recon's go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
Net is go.
RF.
RF is go.
Copy, thank you. MM.
MM is go.
And LDSUP.
LDSUP is go.
The go, no-go sequence is complete. We are currently T-minus 11 minutes and 9 seconds and counting. We go for a terminal count auto sequence at T-minus 10 minutes. From this time, the 3-word hold procedure is in effect.
Greens across the board there from our launch operators during that go, no-go poll, with the team moving ahead with all remaining launch operations ahead of liftoff. Our launch time remains set for 3:15 p.m. local time or 03:15 UTC in approximately 10 minutes 39 seconds. While all eyes are on Electron's launch today from the Southern Hemisphere back in the United States, we have a team working steadily on a mission of another kind for our new big rocket, Neutron. We have the first of our new Archimedes rocket engines on the test stand at the Stennis Space Center in Mississippi, being prepared for its first hot fire in the coming weeks. Now, we'll have 9 of these engines powering the first stage of Neutron to produce a total combined liftoff capacity of 1,485,000 pounds of thrust. In fact, one Archimedes on its own produces the equivalent of about 3 entire Electron rockets. Now, since the engine arrived in Stennis a few weeks ago, the team there has completed numerous checkouts and activations of the test site's infrastructure and its supporting systems. The site's flame stack has been burning bright in preparation, and we can't wait to see the engine burning bright too, with its blue flame mix of liquid oxygen and methane. Here's more from the team at Stennis as they prepare for Archimedes' first hot fire.
I'm Nicky Rains. I'm the manager for RocketLab's facility here at Stennis Space Center. We just installed the Archimedes engine for the first time on the test facility. So we've got engine system integration. There's piping, valving, wiring going on. That's being worked real time with software back in our control room, the human-machine interface, HMI, that we use to control things. Those things are in the final preps and final checkouts. We're ready now to push the engine through final commissioning and ready for hot fire. RocketLab came into NASA Stennis with the lease for the A3 stand. It was a historic stand built for the Constellation program in the late 2000s. We've been able to utilize hardware. We've taken tanks, we've taken valves, existing piping, whole existing systems for gaseous nitrogen, and be able to repurpose those systems and put them to work for what we need. It lets us go faster, it lets us save money, and it lets us get that initial operational capability Archimedes needs. It's great for RocketLab as a commercial company to be partnered here with NASA. We get to use this facility, so we're taking advantage of the existing hardware and being able to repurpose parts of the stand, but we also have a community of support around us. There's contractors here who know how to build rocket test stands, welding, piping, major big concrete and steel structures. There's people who know how to make rocket operations work. So we got that community of people here to support us, and it's a great place to be for a commercial company to be in the middle of this with all that support and the ability to run our operation. My sincere appreciation for the team that we have here at Stennis, the team globally with RocketLab. We've had support from New Zealand and Long Beach and from Wallops. So they've come together here. We put a ton of work in here in the last year, and to see it all come together should be exciting for all of us. The team deserves a huge congratulations from everybody involved that have gotten us this far.
If you want to get in on the next round of engine hot fires, it is not too late to join the Neutron team in Mississippi and California. We have open roles in manufacturing, design, engine development, and more across several states. You should check out rocketlabusa.com for your options. T-minus 6 minutes, 27 seconds to launch. Let's take a look at the Electron rocket for today's mission. Electron is a 3-stage liquid-fueled launch vehicle designed specifically for small satellite missions. And over its 48 missions to date, Electron has deployed more than 180 satellites across various low Earth orbits for science, commercial, and national security missions, including a mission all the way to the moon for NASA. Now, Electron has a lift capacity of just over 300 kilograms to LEO. The rocket stands 18 meters or 59 feet tall, and once fully fueled, weighs 13,000 kilograms or more than 28,000 pounds. The rocket's black look comes from the carbon composite material that it's made of. We use carbon composite across Electron's external structure as well as throughout its internal systems and propellant tanks, which helps to keep Electron as lightweight as possible. Where the rocket looks white is where you're seeing ice form on the outside from the freezing cold temperatures of the liquid oxygen propellant that's being loaded into Electron's tanks. We use a mix of liquid oxygen and kerosene as the propellants for Electron's Rutherford engines. We have 9 of those at the bottom of the first stage and a 10th Rutherford engine that's attached to the second stage. The engines are identical across both stages except for a large expansion nozzle on the second stage Rutherford engine that supports its performance in the vacuum conditions of space. Now, all of our Rutherford engines are 3D printed and battery powered, which makes them unique as far as rocket engines go. Once Electron reaches space, though, it separates its first and second stages to continue the mission to orbit, and then repeats this process again between its second and third stage. This third stage is called the kick stage, and it's what the PREFIRE satellite is attached to all the way through to payload deployment. The kick stage has its own little engine called the Curie, which we use to precisely deploy satellites exactly where they need to go in space. The kick stage will be released at the perigee of this mission's trajectory, which is the lowest part of the kick stage's path around Earth. It's set on an elliptical orbit first, so to course correct to a circular orbit, we wait until the kick stage reaches the other side of the planet and the trajectory's apogee, which is its highest point, close to that 525-kilometre target. Now, once here, the Curie engine will light up to set a circular course around Earth before a few moments later releasing the payload to space and ending the mission for Electron. Now, all of that is coming up shortly now that we are just 3 minutes and 45 seconds until liftoff of PREFIRE and ICE. It's time to send it over to Mission Control to take it from here for the remainder of the count, and I'll be back with you shortly after liftoff. Go NASA, go PREFIRE, and go Electron.
And to all operators, LD and mission code. From now on, there should be no red flags on your critical LCCs. VCON LD mission code.
LD VCON.
Please lock the auto sequence and confirm.
Auto sequence is locked.
VCON, please confirm all expected primary flight computer ASCOs are green.
That's confirmed.
We go for an auto sequence start at T-minus 2 minutes. LDs go for launch.
Vehicle is fully on internal power. AFTSs are green and enabled for flight. LOX load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 and Stage 2 tanks are pressed for flight.
High flow engine purge enabled.
We are T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off.
Beginning pitch over. Stage 1 propulsion.
There goes our 49th Electron rocket soaring off the pad at Launch Complex 1 and on its way to space for NASA. We are now 39 seconds into the mission and our first mission milestone is coming up called Max Q. This is when Electron reaches the maximum amount of pressure that will work against the rocket as it powers its way through the atmosphere. We should hear a call out from Mission Control soon that Electron has made it through that structural test.
High voltage battery discharge nominal.
Cleared max Q.
That's Electron smoothly through max Q as the mission continues. We are now at 1 minute and 18 seconds into the mission as Electron passes more than 18 kilometers in altitude at more than 2,300 kilometers an hour. Up next are a familiar set of actions that Electron performs to continue the mission. The first up will be MECO, or main engine cutoff, when all 9 Rutherford engines on the first stage throttle back before shutting down. After that is stage
Guidance is
separation,
nominal.
followed by the engine startup on Electron's second stage to carry onto orbit with NASA's PREFIRE satellite. Standing by now to listen out for mission control to check off those milestones.
HOS Chathams.
Stage 1 propulsion is holding nominal. Stand by for MECO in roughly 30 seconds. "15 seconds till staging.
Entered burnout detect mode.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
That was MECO, stage separation and second stage engine start for Electron. The second stage Rutherford engine is glowing hot and bright as it carries onto an orbit, now more than 100 kilometers above Earth and moving at more than 8,000 kilometers an hour. Now this engine is identical to the sea-level Rutherford engines used on Electron's first stage, with that exception of a larger expansion nozzle that allows for improved performance. Next up is fairing jettison of the rocket's nose cone. And the fairing is what protects the satellite on Electron through flight. But once Electron is ready to be rid of the nose cone, each half of the fairing is designed to rotate on a hinge away from the payload in a safe separation motion. And that action is due now in just a few moments, so let's listen in.
Fairing jettison confirmed.
And there they went. Electron's fairing halves have split and fallen away from the rocket as planned. Now that nose cone is ejected once we reach space and we don't need its protection anymore for the NASA PREFIRE satellite that is on board. We're heading to a 525 kilometer orbit for this mission, but stage 2 will only take us to just over 200 kilometers to our perigee, where we'll separate the kick stage that has the PREFIRE satellite. So another 100 or so kilometers to go for Electron's second stage. We are approaching the next mark in the launch for Electron's second stage, an action that you'll only come across with our rocket called the battery hotspot. The Rutherford rocket engine powering the second stage uses batteries as the power supply for its propellant pumps. Now, those have been running for some time now, so the battery's power levels are running low. And to prevent an engine stall, we swap out those dying batteries with a fresh pack that will keep the engine running its full duration. Now, those old battery packs are ejected once they're done, which you can sometimes see on your screen as they fall away. So watch out for those just after the T+6 minute mark into the mission.
Throttling down.
Battery
Hot swap
jettison
success.
confirmed.
And that is battery hot swap confirmed for the second stage Rutherford engine, called out by the operator in mission control, in which we saw
Stage
on
2
our screen
propulsion
just
still
moments ago.
holding nominal.
Now, with that clean swap, the Rutherford is continuing nominally along its journey, maintaining its current trajectory towards that perigee and moving along at more than 15,000 kilometers an hour. We have a couple more minutes to go with Electron's second stage as we approach its final set of actions, with engine shutdown and stage separation expected soon after we tick over 9 minutes into the mission. Seven minutes and 10 seconds into the mission, well over 17,000 kilometers an hour now, and things are looking nominal for that second stage engine burn. The next milestone for this mission will be the second engine cutoff on that second stage, which we're coming up to in just a few moments.
High voltage battery discharge holding nominal.
Stage 2 propulsion is holding nominal.
It's now 8 minutes, 16 seconds into the mission, which means we are coming up on the engine shutdown for Electron's second stage, to be followed shortly afterward by stage separation of the kick stage that is carrying NASA's PREFIRE satellite. The process is practically the same as the first stage engine shutdown and stage separation that Electron performed earlier in the launch. We'll know that it's been successful when we see that red hot engine nozzle on the screen start to turn cold with that successful engine shutdown. We're waiting though on the call out from mission control for confirmation of those actions.
Guidance is in terminal, 20 seconds remaining.
Seco confirmed.
Stage 3 separation confirmed. Nominal transfer orbit achieved.
Successful engine shutdown and a clean stage separation for Electron. The kick stage has been released at its perigee with its attached PREFIRE satellite ready to join the first PREFIRE satellite deployed to space just last week. Now, with the kick stage released onto an elliptical orbit first, it now has to complete its first set of maneuvers to correct to a circular orbit. This involves an engine startup in about 40 minutes once the kick stage completes its first half orbit of Earth. We'll take a break in the webcast now, but come back live for that engine startup, as well as the final milestone for this mission, payload deployment for NASA's PREFIRE satellite. We'll see you back here soon. Welcome back to the webcast of our second Electron launch for the NASA PREFIRE Climate Change Mission. Earlier today, our 49th Electron rocket lifted off from RocketLab Launch Complex 1 in New Zealand with its NASA satellite on board for a clean ascent through the usual launch milestones, including max Q, first stage engine shutdown, stage separation, and second stage engine start. After a nominal ascent with the second stage to the mission's target perigee of over 200 kilometres, the kick stage was separated and has just completed its first half pass of Earth. We're now approaching the startup of the kick stage's Curie engine to reposition the stage to a circular orbit. The full duration of the engine burn should last for just under a minute. So let's listen into Mission Control for confirmation for that Curie engine startup.
Curie ignition confirmed.
Curie engine startup confirmed there by Mission Control. That will mean the kick stage is now out of its initial elliptical orbit and onto its 525 kilometre circular path ahead of the payload deployment of the NASA PREFIRE satellite. The kick station's propulsion system includes both our own Curie engine and 6 cold gas reaction control thrusters that enable the stage to perform orbit manoeuvring and positioning like it is now, plane changes, and also orbit lowering burns for when we want to speed up the kick stage's timeline in space. Now, Curie is tiny compared to the Rutherford engine, but like the Rutherford, it is also a 3D printed engine that's integrated with lightweight carbon composite propellant tanks. We also heard over Mission Control there that we have had the successful shutdown of the kick stage's Curie engine, and that means we are now only moments away from payload deployment for NASA's PREFIRE satellite, set to be delivered to its 525 kilometre target orbit to begin its mission to collect data.
PREFIRE 2 deployment confirmed.
Welcome to space, NASA PREFIRE. That is payload deployment complete for the second of 2 satellites for NASA's PREFIRE mission. Now, the second PREFIRE satellite will join the first on its collective mission to monitor the heat lost to space from the Arctic and Antarctica. So, congratulations to NASA and to the RocketLab team for another mission success for Electron. That is 49 Electrons launched, now only one more to go to reach Electron's 50th launch milestone. And we'll have details about our next mission available in the coming days, so keep an eye out on our social media channels and our website for the latest. But until then, thank you so much for joining us for today's launch. This is RocketLab Mission Control signing off.